Good morning all and welcome to Mission Control. Today I'm going to launch this supercapacitor pack into the stratosphere. Well, actually I'm going to charge it up to 24 volts because this is a 24 volt supercapacitor block. Now you may have seen this on my post bag. I think it was 129. This was supplied very kindly by Banggood. It's a 9 supercapacitor block. Voltage is 24.3 volts. These are 2.7 volts, 100 farads each. So of course the combined capacitance, since these are all in series, is 100 divided by 9, so it's 11 or 12 farads as a complete block, 24.3 volts. Now this has 9 protection circuits on it, and they have LEDs, so I'm expecting these LEDs to light up. And let's have a bet now. What colour are these LEDs? Want to guess? We'll see that later on. I've made up this little twin bulb thing which I can sit across here. In fact, it was sitting across here all of last night to discharge this capacitor bank. But we can also watch the voltage come up on those. We can also watch the voltage coming up on my buck converter power supply, because I've decided this time not to put an anti-backfeed diode between my power supply and the supercapacitor. So the voltage on the supercapacitor is going to backfeed through the power supply, and it does from the output back to the input. And I'll talk a little bit more about that as we go through, as I start charging this thing up, because I don't really see that as a problem now. I was going to charge this supercapacitor bank with this thing, which is the Rui Deng. Now, what model is it? Yes, it's the DPH3205 buck boost. So, as I understand it, there's a boost section from the input, which takes it up to a certain voltage. That might vary, actually, depending on how the output is set. But then it's followed by a buck converter to bring the voltage down to whatever you want at the output. I'm going to do something very, very similar. I just didn't want to fry this in case not having an anti-backfeed diode was a problem. But as I said, I don't think it is. So I probably could use this. But I'm going to use my, this is the oldest boost converter I've got, I think. This one can boost up to 80 volts. I've set it for 30 volts. It's the 600 watt. If you want to search for this thing, it's 600 watt boost converter. And then this is the what's it called? 3603, I think, 36 volts, 3 amps, buck converter, but digitally controlled. Anyway, let's get on with it. So because we need to get this up to 24 volts, my incoming power supply from my solar power system is currently only 12.3. Really struggling at the moment. We've got so little light, no sunshine. So I've been having a few issues with this, actually, this dipping down because the batteries outside just aren't very well charged. So 12 volts or thereabouts in, 30 volts out. That's going into my buck converter, which I've set for 25 volts and 300 milliamps. That should be about right to get the timing of this charge right. Let's switch on. And that's looking at current, that's the 300 milliamps. That's looking at voltage. There really isn't a lot of voltage on this thing at the moment. Right, we're up to 1.3 volts. Now let's talk about backfeed, because this power supply is essentially a buck converter. So a simplified diagram of it is this. So if this capacitor is charged to, say, 24 volts, is it going to backfeed back through the buck converter? Well, it looks like it wouldn't if this switch is open, but you've got to remember that this switch is a MOSFET, and the MOSFET has a body diode, and it goes in that direction. So, yes, we are going to get a backfeed of the voltage on the supercapacitor block back through the inductor. The diode won't do anything, but it will go back through the body diode of this MOSFET and will appear at the input of the buck converter. Now, there are some advantages to that, and I'll show you that in a little while. Have these bulbs come on yet? Oh, they're just glowing ever so slightly red. So we are going to get the voltage from the supercaps backfed through the buck converter to the input. Now, the input of this buck converter has a regulator which provides power for the microprocessor, microcontroller, and the digital display. So when we get up to about 5 or so volts, that's actually quite handy because the SuperCap can run the power supply without having anything plugged in on the input. Now, of course, it doesn't do anything, but it does work as a voltmeter, so it's quite handy. And this is the reason I don't want an anti-backfeed diode in this connection between my power supply and the SuperCaps, because I want the voltage on the output of the power supply to be the capacitor voltage. If you've got a diode in here, then you're not seeing the actual voltage across the capacitor. This is much better representation of what's going on here. Right, so I'm just printing out the boost converter article from Wikipedia. We're up to 5.3 volts. I think you can probably see these lamps are glowing now. That noise is my printer printing the boost converter article. So yeah, the voltage on this is coming up. Need to take it to 24 volts before the little LEDs on there guess the color before they start coming on. Right, now let's take a look at if I backfeed voltage from the supercapacitor back through the buck regulator to its input. What happens to about backfeed back through the boost converter? Let's take a look at that. So here's the simplified schematic of the boost converter, and if that's off, this switch will be open, and you'll see that we can't backfeed through this circuit because you can't go backwards through this diode. So there will be no backfeed back through the boost converter. And let me just switch off the boost converter now by pulling that plug. And we should see the voltage on the supercapacitor go down because, of course, we've got no power feeding through. But yeah, this just acts now like a voltmeter because the voltage on the supercapacitor is back feeding through this power supply, keeping the microcontroller and the display alive, and the system that's measuring voltage is simply measuring the voltage at the output, and that is the supercapacitor voltage. So yeah, a handy little voltmeter. But anyway, I'm charging this, not discharging it, so let's plug my 12 volts back in, 30 volts, that's feeding my power supply. Supercapacitor voltage continues to rise. So I think I'm satisfied that using a that's a boost buck configuration to charge a supercapacitor, I'm not concerned now about the notion that energy might backfeed from the supercapacitor back through my buck regulator and my boost regulator. Certainly can't do that on the boost regulator. And so yeah, next time I probably would go for this thing. The only reason I didn't want to use this is because it's quite expensive. This module is cheap now, so I kind of thought, well, it can be sacrificial. I can sacrifice it if there's a problem, but I don't think there is a problem. Let's take this on up to 24 volts. Now, once this thing reaches 24 volts or thereabouts, the protection circuit should start coming on. That means that this device is going to be dumping energy into these resistors and they'll warm up. And I want to actually visualize that. So I'm going to use the HTI HTA1 thermal imaging camera. Let's switch that on. But I really need to update you about this thing because there's one issue with this. It's a very useful thermal imaging camera, particularly for me because of the high resolution sensor and this flat format, so I can bring it up to my camera that I'm filming. What am I looking at there? Oh, I think I'm looking at my buck converter there. Yes, that's the supercapacitor bank over there. You can see the two lamps. But the issue I've had with this is that every time I come to switch it on, the battery's flat. So I've got a funny feeling that this has some sort of parasitic drain on the battery, and after a few days, I think it is, it's just completely depleted and you need to charge it up. So it's a bit like old nickel cadmium power tool batteries. Whenever you come to use the device, battery's flat. But apart from that, this has proved to be pretty good so far. So let's try and move the camera a bit so that I can focus in on the supercapacitor module. Right, I've moved the camera over a bit. Let's have a look at that. I ought to turn my light off. I'm going to do that because it's reflecting on the screen. Right, so we can see the supercapacitor module. You can clearly see the two light bulbs there. They're hot. On the supercapacitor module board, we've got various components. There isn't much of a temperature difference between, in fact, that's quite likely to be an emissivity difference between the matte black components and other elements on the board, but certainly none of those protection circuits are on because none of these resistors is yet warm. Okay, where are we? Getting towards 12 volts. Now, of course, I'm throwing energy away in those light bulbs, aren't I? So let's take those off. That's a bit daft, really. This will charge a lot more quickly if I don't have those light bulbs. And we're still waiting for those LEDs to come on. Now, shall I do one of those really long shots, which I'll just speed up when I run the editing software? Windows Movie Maker, yes, it's not very good, but good enough. I am looking at alternatives. Yes, I think I'll shut up now. Let this continue to charge up closer to 24 volts. Speed it all up in post. I've just upped the current to 500 milliamps just to make this process take a little less time. So yeah, I think that's running a bit quicker. Now this power supply is current limited, so it's running at a constant current. At the moment that is 500 milliamps. And of course, as the voltage goes up, that means that the power draw is increasing. So it's drawing more and more power from the boost converter. You can see that the voltage on the output of that is just falling back ever so slightly. And actually my voltmeter on my solar system is reading now 11.6. So it's struggling a bit to provide the power for this system. I might back this back down to 300 milliamps because I know that the solar power system is really struggling. No, that's something, that's the voltage. What was that set to? That was set to 25. Yeah, 25 is about right. Let's switch it to current if I can. Pull that down to 300 milliamps again. Yes, the output of the boost has upped a little bit. Let me actually save that. I'll just switch it off and save it. 25, 300 milliamps, switch that back on. And we're at 21.2 volts. Let's carry on going up. I can see some LEDs starting to come on, notably that one, which is a sort of, well, I think it's red, but it's a bit of a orangey red. Let me get a shadow creating thing. And yes, we can now see various LEDs coming on. I think I can see 8 in total. Let's just move the camera back over here so that I can get the thermal imaging camera on this. Switch this back on. There we go. Right, let's have a look at these resistors. Now, just get an idea of where these resistors are. There are 3 up there. There are 2 in close proximity here. And 2 in close proximity there. So let's just take a look at those. And yes, we can see those resistors as white highlights. I can also see the transistors, I think. The MOSFETs that are controlling those resistors. But let's see if we can count the resistors. We've got 2 here, another 2 there, another 2 there, 1 and 1. So we've got 8 of the 9 protection circuits have come on, and one of them hasn't. This one here in the middle of that top row, got 3 resistors there. Let's see if we can see those 3 resistors on the board. Well, no, we can only see 1, 2. The one in the middle, this protection circuit in the middle has not yet come on. I think I need to get the DVM out to measure the voltage on that capacitor to try and see why that protection circuit hasn't come on. Let's switch that off just for the moment. Certainly haven't got the 24.3 volts that this thing should be at if all the capacitors are at 2.7 volts. So let's just measure this one. Be careful with this because these things have a habit of slipping. Oh, the whole thing's slipping. I think I can put my hand on here. The resistors are quite warm. It's a bit tricky. Yeah, now you see that capacitor has only got 1.6 volts across it. So we've got a really lazy cap here. Let's measure one of the ones where there's a light on. I can spike the probes into these bits of solder. 2.6 volts across that one, and I'd imagine we've got a similar voltage on all of these. Yeah, it's getting quite warm, this board. If I touch, yeah, that's 2.6 volts as well. But this one, let me just take out the little thing I had to angle that up because it's not helping me. But this one at the back is only 1.6 volts. So we've got a really lazy capacitor here, one that's just not come up with all the others. And I have had this on all the SuperCap boards I've tested. There's always a slow capacitor, one that's miles behind the others. And it takes a long time to sort of condition these boards to bring that last capacitor up. So it's probably going to have to sit there for quite a while before that capacitor gets anywhere near 2.7 volts. It's only at 1.6 at the moment. Now, the other thing I've noticed about this supercapacitor protection board is that the capacitors get quite warm after a while. And if I zoom in, you might be able to see why. The resistor that the MOSFET connects across the capacitor terminals here is really very close to one of the capacitor terminals. So the heat coming from this resistor, and there's no thermal copper on this board, so there's been no attempt to sort of take the heat away and just dissipate it in a copper heatsink. So it all goes down this track into the capacitor leg, and the capacitor gets really quite warm, and these were getting quite warm when I tested this yesterday. Let's try the thermal imaging camera on that. Right, so here's a view of the capacitors lying down like that. They're at about 30 degrees, a bit warmer near the top. The board is quite hot in that corner. That's probably because there's a resistor sitting in that corner. That's 50 degrees up there. But yeah, this cap here is at about 30 degrees. Now it will get warmer as time goes on. Let's flip this board over and take a look at the temperature of those resistors. Got to get this angled in the right way. So we're looking for max there. You can see max down at the bottom right hand corner as we look at this screen, and it's about 86 degrees, and that should be fairly accurate because those are sort of almost perfect black body radiators, so my emissivity of 0.95 is probably about right. Yeah, 86 degrees on those power dissipating resistors. A little bit more voltage here now, 23.1 volts. Let's have another look at the rogue capacitor, see what voltage it's got up to. Well, 1.8 now, still a long way off the 2.7 volts, which we really want it to get to put the maximum voltage across this whole pack. And my theory about this, I don't know whether you remember, but this thing came supplied with this little piece of wire wrapped around the two contacts to hold the terminal voltage at 0. My theory is that one of these capacitors is pushed into a negative charge state. So that capacitor was pushed into negative charge, and now it's really struggling to take on a positive charge. And I just feel that if these protection boards had an additional component, which is a Schottky diode directly across the capacitor terminals, that would prevent any one of these 9 capacitors actually flipping around and going into negatively charged situation. So I think because this one's got the lights on it, I don't have to do a mod to put LEDs on this board. I'm almost tempted to mod this board with 9 Schottky diodes to try and prevent this negative charge situation, if indeed that's what's happening. Let's just check this capacitor again, and it's getting close now to 2 volts. Is that voltage going up? Don't want to slip with my probes here. Oh, I did slip. Yes, I think that is going up, isn't it? 1.989 and 1.990. So it's still coming up, and I'm sure if I sat here long enough, I could get that up to the full 2.7 volts, and that final 9th LED would come on, but that's going to take a long time, I think. Now I'm just trying to work out how much power these protection circuits will dissipate. We've got a 6R8, 6.8 ohms across 2.7 volts, so it's less than half an amp, isn't it? Now I'm putting in 300 milliamps. Let's put in, say, 400 milliamps and see how the brightness of these LEDs changes. Yes, they're a lot brighter, so they're having to do a lot more work at 400 milliamps. And if I went up to 500 milliamps, I'd probably find that these wouldn't be able to cope very well and actually wouldn't dissipate all of the power coming in as heat, and the capacitors would go over voltage. Let's just check the maximum temperature. Oh, it's over here now, isn't it? I've got to come to there. You can't see the maximum. Oh, well, there it is. 109 degrees is the maximum temperature. Well, that'll be the resistors. So yeah, they're starting to get quite warm now. So I will back the current off to 300 milliamps, and these will dim down and the temperatures will fall away. But I think that's all I wanted to do really, was just to get this thing charged up to 24 volts. Now I know that we're not going to have a backfeed problem, so I can pull out my 12 volts. The 30 volts disappears from the output of here. No backfeed into this module because of course we've got this effectively an anti-backfeed diode inherent in the boost converter. There's backfeed from this module, all the lights have gone out now of course, into the voltmeter. Now we're monitoring current, aren't we? If I switch that to voltage, we can see the voltage across the supercapacitor bank. There's no power supply to my power supply. Well, there is, but it's coming from the output back through to the input. And now, as the final thing, I'm just going to put my little lamps, two 12-volt bulbs. They're nice and bright now because this thing's at 23 volts. And I will discharge this capacitor bank, bring it back down to 0. That capacitor may well go negative voltage. I could check that, couldn't I? Perhaps I'll just see whether that goes negative voltage when the voltage of the whole pack gets back down to 0. Right, this is discharging. I thought you might want to just see the rate at which this is discharging into these two lamps. They're 1 watt each, so we've got 2 watts here, 100 milliamps approximately flowing through those. Of course, it's also powering this module. It's lighting up these LEDs and powering the microcontroller. This can come out. I can unplug that, the boost converter. So this is just running standalone. This is backfeeding by virtue of the inductor and the body diode on this MOSFET. So we've probably got the capacitor voltage at the input of this buck converter. If I shorted across those input terminals, then there's really nothing to current limit, and there would be a loud crack and a spark probably. I could measure the voltage at those input terminals. Let's do that. Let's turn my meter back on. Can we see it? We can see if I put it there, but then that's likely to fall off my desk. Where can I put it that it won't? I'll put it sideways on. You can't see it sideways on. I'll rearrange things. Right, let's just check the voltage on the input of the buck module. And yes, it is there, 19 volts. Is it the same as that's reading? It's a little lower, and that's not surprising because we've got a volt drop across that diode, haven't we? It's probably a Schottky diode. Looks like there's about 300 millivolts difference. So yeah, we'd expect a lower voltage at the input side of this buck regulator, but there's, as I say, no current limiting. If I short these two probes, it would go bang. So still on the discharge, let's measure the voltage on, this is the lazy cap here, well lazy, slow to charge. Let's measure the one just below it, and that's 1.8. Let's measure the lazy one, or the slow one. Yeah. Oh, that's down at 0.6. That could easily go negative when the others get low. Let's measure this one up here. 1.8, the same. So yeah, this one's just at a much lower voltage. The balance is just way out. Now it's just occurred to me that I can use the backfeed through my power supply with this set of 3 bulbs soldered to a plug. Yeah, I can use that to discharge this through that power supply. It will be going through the inductor. Now, how many watts is that? That's 15 watts. But I mean, this thing can... Oh, let's just do it. So it's effectively a dead short, but that's going to bring the voltage down quickly. 13, 12. Yeah, so I'll leave that in for a bit to discharge. Can't see those bulbs, can we? To discharge this capacitor block a little more quickly, and then I'll have another measure of our lazy capacitor. So those bulbs have brought the voltage rapidly down to about 6 volts. Let's take those off now, and I'll measure these again. Now I seem to remember it was positive to the bottom. So positive to the bottom. This one is 0.7. This one at the top should be the same. 0.79. And this one in the middle. Ooh, has it gone stay on there. Ah, it has gone negative. Look at that. It's not much. It's only 300 millivolts, but it has gone negative. That's not ideal, is it? No, that's really not ideal. Now, a Schottky diode, it has a forward voltage. Oh, no, is it lower at low current? I can't remember, but it's about this sort of voltage. So it hasn't really gone negative enough for the Schottky diode to do anything. So that wouldn't help at the moment. But if that goes any further negative, then perhaps a Schottky diode would help. I'll wait until this thing gets right down to nothing. Right, so the voltage on the supercapacitor bank is now so low that the power supply has just gone funny and it's just showing a 0. It's obviously crashed, so it's not acting as a voltmeter anymore. Let's voltmeter these caps again. I'll just do the bottom one and the middle one. We've got 0.575 and the lazy cap, the reverse polarity cap. Yeah, so that's now at minus 400 millivolts. So a Schottky diode might help. It might help. I think I might put that on. Well, there it is. A full charge and discharge of this CSD well supercapacitor bank. 9 capacitors in series with 9 protection circuits. For the moment, that's all I plan to do today. Cheerio.